Dzień dobry. It's a good start, but I am going to speak in English. So if there's anything you don't understand or you would like me to slow down, then please let me know. My name's Andy Mason. I'm delighted to be here. Dwave and the university have just signed an agreement whereby we will look to contribute towards the university becoming a centre of excellence. You want me to hold this? For the university to become a centre of excellence for quantum computing in Poland, and obviously for having European aspirations. Effectively, Dwave, the company, was founded in 1999, and although quantum mechanics and quantum physics has been around for a long, long time, the holy grail of making a quantum computer was always seen as a very difficult prospect, and was always one of those projects that was always going to happen in 10 years' time. Researchers were researching, and when you said, when will we have a quantum computer, the answer was always 10 years' time. So in about 2011, Dwave delivered the first commercially available quantum computer to a large American defense contractor called Lockheed Martin, and they got the world's first quantum computer, and it's been in operation for the last 5 years. So we've actually broken the tradition of academia and research getting to a quantum computer, and we've actually designed ones ourselves. So when we talk about quantum computing, people always will ask, well, what is a quantum computer? So I don't know whether you're physicists or whether you're engineers or mathematicians, but you will all have come across a demonstration of quantum mechanics in everyday life. And that's basically the biggest example is a laser. But typically, we all see quantum effects, but they're small and they're unstable. And in our PCs and laptops, then the quantum effects that take place in that sort of device are bad for it. So we try to eliminate all of the quantum effects we can. Otherwise, we get errors in memory, we get bit flips, and we get lots of errors within a normal computer. But a quantum computer actually harnesses the effects of quantum mechanics and actually uses them to do a different type of calculation, a much more powerful calculation than we could do with a classical computer. We really want to exploit the quantum mechanics, and we actually have things called qubits, quantum bits rather than bits, and we operate in a very extreme environment to gain the stability of the system, and I'll touch on that in a minute. So what are the effects that we use from quantum mechanics? First of all, there's something called superposition, and this is probably the most famous quantum effect, and this is where something can be in two states at the same time. Schrödinger has an example of a cat in a box, and basically asks the question, is the cat alive or dead? And actually, in a quantum mechanics effect, then the cat will be both alive and dead, and it's only when you disturb the experiment by opening the box that you find out whether it's dead or alive. In the same way, we have we treat bits from a mathematical point of view, and we can have them as both a 0 and a 1 at the same time. So if you can imagine, I'm carrying a bucket, and I've got a bucket full of 1s and a bucket full of 0s, then I can only transport a certain number in a classical environment, because each piece of information is singular. It's either a 0 or it's a 1. If you imagine now I've got the buckets full of qubits, the same number of qubits will actually have double the amount of information, in fact quadruple the amount of information, because I have a 0 and a 1 at the same time. Okay? That's what superposition is all about. We then have something called entanglement, and we've all heard of Einstein, and Einstein, with all his brain power, he called entanglement a spooky effect at a distance. And like most quantum mechanical engineers, we don't actually really know what's going on in entanglement. What entanglement in simplicity means is the fact that two or more qubits can associate with each other, and you cannot describe one of the qubits without having to describe the other. So that may sound a bit fanciful, but if you can imagine that if you have a calculation that is carrying a lot of information and you want to change a bit in memory and you want a bit over here in memory also to change at the same time, then if those two act as one bit, then that makes your calculation go a lot faster, because you just need to change this one bit and then multiple bits will change in the future. So that's something called entanglement. And lastly, we use the phenomenon of quantum tunneling to actually allow us to do searches and large optimization problems in a much faster way. So there's a concept here of the idea that my qubit on the left-hand side, this left-hand ball, in a classical normal situation, for it to get over that barrier, we need to raise the energy of that qubit such that it has enough energy to go over the barrier and down the other side. So the qubit needs to be given, in a classical environment, needs to be given a lot of energy to actually get over that barrier. So in a quantum environment, that actual qubit actually will tunnel through. It understands that there is a lower energy place behind the barrier, so it will tunnel through the barrier itself and end up in that lower state. So that's sort of like in a very, very quick nutshell, that's what quantum computing is. So what have D-Wave done? So D-Wave, all of these black devices, I hope you can see those boxes, they're about 3 meters by 3 meters by 3 meters, and they contain the quantum processor that we've developed to do the quantum calculations in our computer. It's an extremely harsh environment, so you can read the facts there, that it is actually 175 times colder than interstellar space. Some actually say that it's probably the coldest place on Earth, because we actually cool the quantum processor down to something like 12 or 15 millikelvins, which is 12 or 15 milli-degrees, shall we say, above absolute zero, which in centigrade is 273 degrees. So we're operating this computer at minus 272.8 degrees, or whatever the maths is. So very, 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 very cold. It has to be in a very, very large vacuum, and what we can see here, this is inside the box over here. And if you can see that comes up, you can see the various temperatures as we go down this platform, which is a dilution refrigerator. And the actual processor itself is right down here at the bottom, sitting there at that very low temperature. And we have to make the temperature very low to get superconducting effects and allow us to operate in a no power environment. So it's a very, very fragile situation. And this is what has made quantum computing so difficult, because we have to have it in this environment. So this is the processor itself. That's a sort of enlargement, and that's where we do the calculations. So that's kind of like a very, very brief overview on quantum computers, a description of what would D-Wave do. And the important thing that we have now is the fact that we need to program this quantum computer. Okay? So if you imagine in your laptop processors, you have probably, you're using an Intel instruction set to understand the language and how to operate with that program. And that operating set is probably in the order of 500, more than 500 operations. So I'm talking of things here like adding, multiplying, subtracting, and all those sort of things. Well, in the quantum computer, we only have one instruction. It's quite long. It's about 4,500 characters long, but we only have one instruction. But it's a very, very powerful instruction, because we can actually search a search space of something like 2 to the 1,000th. So anybody, any guesses as how big 2 to the 1,000 is? Big number, huh? So let me just tell you that 2 to the 300 is about the same number of estimated particles in the whole universe. So we're actually searching a search space that really is the size of the universe inside another universe inside another universe. So it's a huge, great search space. So okay, so what are we going to do with all that power of searching those search spaces, and how are we going to program it? So effectively, let me give you an example. Let's assume that we have 1,000 qubits, and our 1,000 qubit processor, and each qubit represents a sports player. So I like football. I support a team in England called Southampton, who won the other night. So we're going to go with football. And the objective of this problem is to choose the best 11 players out of all the 1,000 players. You see where the numbers are coming from? So we have the 1,000 qubits, and so to each qubit, we assign a value in terms of how good that player is. So let's say it's a value 0 to 10. A particular guy scores lots of goals, passes it very, very well. He's very valuable. We'll give him a 9. Another player may not be quite so good. He's a defender, doesn't score goals a lot. We'll assign him, shall we say, a 5, a weight of 5. And we do this for all the 1,000 qubits, okay? So we've now got a big problem to decide how do we work out who is the best player. But not only that, we also want to know who plays best with somebody else. So we might have the original guy that we gave 9, might score lots of goals, does great passes, but whenever he plays with the guy who only got 5, they always win, okay? So we give the idea that this player and that player, we want to be on our team. He's only got a 5, but these two combined always win. So we do that for the whole matrix of 1,000 qubits, and we effectively, that is our quantum machine instruction that we send to the machine. It then chooses 11 of the players who will be probably the best fit, because in an optimization problem there isn't a real answer, probably the right answer, and that will be our best team out of the 11. And as you can imagine, there might be more than one good answer, and we then have to do more statistical analysis on that to work out what that answer is.
So, are there any questions for Andy at this point? So actually, I have one, if I may. So people probably are wondering right now what quantum computers, Dwave, and programming languages like Python, for instance, have in common. Could you please elaborate on that a bit more?
Sure thing. So I don't know where you are in your computing careers, but obviously I imagine that you have touched and dabbled with things like Python. The actual programming of the quantum computer is a bit like being back in the 1950s, 1960s, which I'm not too sure many of you will remember. But in those early days, you had to program a computer by talking to each of the transistors or the gates and doing it on an individual basis. And that's very much what we started off doing with the D-Wave quantum computer. And as time's gone by, we then introduced tools and patches and libraries that enable us to simply write in a program like Python or C or C++, so that we can actually translate known languages through into that quantum machine instruction that I was talking to you about. So there's a little bit of the known and there's a little bit of the unknown. And it's a very, very exciting area to be in, because we're very much on the forefront of both science and the forefront of computing.
So it's like you have this very powerful machine called quantum computer, but you still need to use classical computers to program it. Isn't that correct?
Absolutely, yes. So right now, then, we actually need to create that quantum machine instruction. And so we do that by programming a front-end server that actually talks to the processor chip itself. So the processor chip looks like one of these, not the whole thing. There's about 150 different processors on here, and they all work in this quantum manner. So we need to actually translate from normal human interface, us thinking about something, through to the actual program that we're going to write in a known language, and then that gets translated into the quantum language, so we can then make best use of these quantum instructions.
So wouldn't be fair to say that knowing Python is probably the very first step to learn how to program quantum computer, D-Wave?
Absolutely, yes. Yes, a good mathematical background and the ability to program in Python is very, very important from the point of view of getting on and making the best use of one of these systems.
Thank you.